Hey guys, Joe Pye here at Advanced Innovations. Welcome back to the shop. Today's video is very technical and a little long-winded initially. So if you just want to see chips fly, well then fast forward through all the digital stuff in the beginning and just go back to where the machining is. But if you really want to learn something new, a new technique, well not really a new technique, but an existing technique, then suffer through the beginning because it's detailed, it's technical, and it's valuable. It'll help you out. Anyway, today's video is inspired by a video that I recently watched by another maker named Alec Steele. That's Alec with a C, Steele with an E on the end. He's a blacksmith, he's young, he's got a lot of energy, and he's building a miniature steam hammer. And in his kit, he got some elliptical material. Now, an ellipse is not something that is easily achieved on a machine that only moves left and right, in and out, up and down. It is a little bit more technical than that. There's a lot of math involved, there's a lot of setup involved. The part can easily be done if you have an XY vise on your rotary table. That makes life a whole lot easier. But if you don't, well, then you're just going to have to do it the old-fashioned way, and that's what I'm going to show you today. So the first half of this video is going to be how to center up the material, the logic behind the positioning of the part, followed immediately by the math involved, showing you how to determine how far to rotate for all the different radius, tangent points, and such, yada, yada. Boring AF. But a necessary evil if you want to throw chips and have a part that looks pretty good. Anyway, let's move on to the digital animation and take a look at how that's done. Hope you enjoy this one. Okay guys, before we get started, I want to cover a couple of very basic rotary table setup facts. This part is going to be moving around a bunch once it gets to the rotary table, and I want you to have some type of comprehension of exactly what's going on. The big round part in front of you, that is the rotary table model that I've created, and the little green part in the center is the ellipse that will be done on that table. The red represents the end mill and the spindle of the machine. So let's just get that out of there for a second. You can see that the ellipse that we're going to create has 4 protrusions on it. Those protrusions represent the axes of each feature. On the rotary table model itself, there are 2 curves drawn on. This line right here where the mouse or the cursor is jumping around, and the small one in the center. They represent the radii that will be machined onto the part when the part hits the table. Now let's see if I can grab a hold of that piece and show you how this part is going to bounce around on that table. The first radius that I'm going to cut on this piece is the one facing away from me as the part is positioned on the y-axis. And you can see if you take the little protrusions that I've drawn on there representing the axes of the feature. Let's go for wireframe. That the part lines up very nicely with the radius drawn on the table. Okay, so anytime you're going to put a round feature on a part, the center line of that round feature absolutely must be over the center of rotation of the rotary table. That does not guarantee that dimensionally the radius is going to be the correct size. That just guarantees that it's going to be in the right spot. The dimensional conformance of the feature will be determined by the placement of the end mill. If the end mill is a little too far out, naturally the radius is going to be bigger. If it's too far in, now it's going to be smaller. So the size of the radius is dependent on the relationship between the center of the rotary table and the center of the end mill. The placement or the accuracy of the feature, like I said, depends on the part to the rotary table relationship. And for the end features, it will be thusly. Let's see what that looks like from above. Make sure that the axes of the feature are in line with the rotation point on the rotary table. Now when I bounce this part around on the table, once I start machining it, and it will move forward and backwards initially, and then it will go back to center, and it will move left and right to do the ends. When you do this, the rotation of the rotary table is going to be very sensitive. The setting of the end mill to the rotary table is going to be very sensitive. And right here on the ends of the part, where the tangent line is, where the tangent point is, that's a very sensitive area, and the chances are you're going to end up with a small dig or bump or dimple or something in that area. And of the 4 opportunities that I had to get it right on this part, one of them did present a small dig, which was easily removed with a file. Next question I'm sure is going to be, how do you figure out the rotation? You can see that I did a CAD representation of the angle of the tangents up here. Let's get that in the center. So using CAD, it's a piece of cake in order to figure that out. But if you got to figure it out with a piece of paper, I'm going to show you how to do that just before we start cutting. All right, so let's get out to the bench. I'll draw you a quickie little sketch on how to figure out how far to spin the rotary table in a setup like this. And I'll make some chips. Let's do it. All right, let's take a look on how to figure out the rotation of the rotary table to find the tangent points for the end cuts. Okay, end cuts. I'm going to start off with the representation of the major diameter. Okay, this is a 2-inch circle or a radius of 1 inch as called out on the print. I'm going to establish the center point of this particular drawing right here. And I'm going to strike a 1-inch cord, or a 1-inch, yeah, it's a 1-inch cord, straight to the edge of the part. We'll call this A, we'll call this B. AB, 1 inch, because it's a 1-inch radius. Simple. Here comes the center line of the part. We know that the part is 500 thick. So we're going to call this C. That makes BC 750. BC 750. Why? Because AB is half the part. The part is 250 per side. So now we know this is 0.750. Triangles are starting to jump right off the page for you. The distance from the center line of the part to the center of the end tangent radius is 424. Let's call that D. Well, we're not going to call it anything right now. I'm just going to call it 424. Okay. So now you have 2 legs of a given triangle, 750 and 424. Realistically, that is all you need to calculate the sweep angle for the rotary table movement. Let's take a look at the geometric rules that will fall into place here. I'm going to connect B. Well, let's call that D. What the heck, right? I'm going to connect B through D and watch what happens. Where the centers of these 2 arcs connect and project, this point right here is the tangent point of that end radius. So as the top radius comes around, it's going to stop right here, transition to the small radius, and come back around. Now, also by geometric construction, let's project these lines out a little bit further so you can see this. Whenever you have lines that cross over like that, they form 2 sets of identical angles. This angle on the outside is equal to this angle on the inside. And you can see if that was a scissor and you started moving it, they would pivot around this point, and these angles would always be the same. Because if you laid this flat, it would be a straight line, right? So open it up like a butterfly. These angles are the same. These bigger angles on the outside are also the same. So once you figure out what this angle is right here, you know how far that rotary table has to move based on this rule right here. And that particular angle, depending on what you work with, you can also figure out what this leg is here if you want to figure that out. That's 1 inch minus the radius of the smaller circle. That turns out to be 862. So in the long run, you have a triangle that you have all 3 sides of, and you can pick your poison, which trig formula you want to use to figure that out. This being the angle that you want to find out. That's your rotary table sweep right there. Now be careful when you bring the cutter around. Chances are it's going to dig, hit, depending on the flex of the cutter, the accuracy, the setup. 99 different variables are going to cause that to leave a mark. And if it happens, no big deal. That's why they invented files, right? You can file out the bump, file out the blemish, do what you need to do to make it pretty. But that's a very, very sensitive setup to get tangent arcs like that, especially 3 tangent arcs. Chances are one of them is going to leave a mark. Out of the 4 that I did on the part that I'm going to show you, one of them did leave a mark. I did file it out. So no shame there. It's not as tough as it looks. Remember that. Take a snapshot of that and put that in your toolbox. First step in this process is to make sure the table is true to the spindle. Now, since the center hole isn't doing the work and the motion of the rotary table is, you've seen me preach this 100 times, disconnect the worm on the table, spin the table, track the spindle. When those 2 line up, all is well. Zero out the digital readout right now. I'm going to return my table to the X0 position, and this rail on my rotary table is true to the world, true to the X-axis position. That's a very important place to start. Okay, let's get on with the rest of the components. Now this is a setup that you're going to be seeing in your sleep for a very long time. If you attempt to do this, you're going to be scratching your head and probably walking away from the machine about 9 times. And believe me, it's justifiable. I have gently Sharpie markered the profile of the part on this block just to illustrate exactly what I'm trying to convey here. The left-right shift for the end radii will be established by a stack of gauge blocks between the side of the vise and a stop on the table. I can move the vise a precision amount this way, and I can move it back to center, and I can move it a precision amount that way and back to center. I've got the same ability to move the part on the y-axis in and out with the use of 3/4 inch parallels in the back, right there. So if the part is going to move incrementally exactly the same amount in both directions, starting on center, you would be required to have a spacer of the shift value against the fence at that time. When I want it to move, I'll just remove this, and this slides in. And when I want to bring it back out beyond center to the second position, I will add a second parallel. Stick it back in there, contact, away you go. Same thing with the side. Remove the shim, over it comes. When you go back, the same size shim will get you back on center. Double the thickness of the shim. We'll take it to the second position. So there's a lot going on this part. This is something you may have to watch 1 or 2 times. But I'm going to see if I can track the stylus on the line that I printed on this part with a single parallel in the back and a single stack of blocks against the side stop. That stylus is now on 0. I'm going to set the 1 inch radius by moving the table. The rotary table, the Bridgeport table, everything is going to move 1 inch in that direction. Now when I actually make the cut, depending on the size of the cutter that I use, I will have to accommodate that 1 inch shift to allow for the diameter of the tool that I'm going to use. So if I was using a 1/2 inch tool, I would have to move 1 1/4 inches to allow for the radius, okay? Now in order to put that cutter where I want it, I have to double up on that back shim and move this surface under the cutter. And now by sweeping the table with the position of the part as is, you can see that the radius stays on that line. The backside radius will be done exactly the same way. Table moved in that direction, shims taken out. Table back to 0. Table at 1 inch. Not a problem. Now believe me, the first time you try this, you're going to step back from the machine, you're going to scratch your head until you have a bald spot, and then you're going to decide to do something else, because this is not easy. But comprehending the movement of a part versus the position of the rotary table to the spindle, once you get it, it's like an aha moment, palm to forehead, I finally see it. So let's clamp this thing down and see if I can make that cut, and then we'll worry about blending in the tangent end radii, radiuses, wherever you are in the world, whatever it is you, however you say that. That's what we'll do next. Let me swap out the drill chuck, swap in a cutter, and we'll make those cuts and see what it looks like. I'm using a 250 diameter cutter, so my digital right now is set at 1 inch 125. I want to make a rough and finish pass, so I added 30 to that. The digital is now positioned at 1 inch 155. I am 30 thousandths away from final. I may nibble at this, peck at it, who knows what I'm going to do, but I'm going to get the material out of there so we can see if the radius is going to fall where I hope it is. Looks good. Let's do it. By climbing on all those plunge cuts, the cutter will flex away from the part and not leave deep vertical lines in the part. If I were to conventional that thing would look like a curved staircase right now with all the lines that would be in it. 30 thousandths away from final, so let's take a couple of finish passes, clean that surface up, and we'll spin it around. After we clean up the mess that's on the rotary table. Good gracious. All right, let's do it. First side radius complete. Real time, approximately 6 minutes from the start of this particular video segment. Blow it all off. I'll show you the second side setup, and we'll cut the other side exactly the same way. First feature is complete. Let's move on to the second feature. First thing I'm going to do is release the clamps on the vise. Do not move the part in the vise itself. You can move the whole vise, just don't move the part. Going to return the table to the 0 position. Right now the rotary table is true to the center of the cutter. Okay, let's move that cutter closer so you get a better feel for what's going on. Now when I return the cutter, the vise back to the original 3/4 inch offset, You can see that the cutter is now over the center of the part. What I need to do is I need to get the center of rotation of the new feature over the center of the rotary table, okay? The feature itself has to be centered over the rotary table, and then everything else should fall in based on where the rotary table is pushed to. But the center axis of that feature, the new feature, must be over the center of the rotary table. Makes perfect sense, right? Like the center axis of a wheel. And the only way to do that right now is to add another shim behind it. So now I have two 3/4 inch shims back here. At this point, the center of this arc is directly under the center of this arc is directly over the center of the rotary table. So it's basically dealer's choice, however big you want to make this feature, the center of that feature will always be over the center of the rotary table. I know this is confusing, guys. I really do apologize. If I figure out a better way to convey what I'm trying to show you, then I will definitely speak it out. I guess a good way to look at it is if we were setting a boring head, the boring head is only going to cut the hole that it's dialed to bore, right? It's going to cut a specific size. Where it cuts that hole, that is up to the position of the table, position of the part. That's exactly what's going on here, and the rotary table is the boring head. So this setup right now is set up to create a very specific radius center line. The size of that center line depends on where I put the table itself. So the rotary table, everything's got to move to give me that number right there. That allows me to do the rough and finish passes and have everything in the right spot. So now I'm going to move off my 1 inch plus the radius of the cutter, which is 125, plus 30 thousandths for a rough cut, which is 1 inch 155, and I'm going to lock down the y-axis of the table right now. And I think you can see that when that cutter comes down, it is going to cut right on the outside of that black line. Going to make a little football here. That's what I'm looking for. I can round the ends off at a later date, and I will do that within this video by manipulating the little side block the same as I've been manipulating the parallels in the rear. Make sure everything is nice and snug. Kill the camera here for a second to secure some clamps and be right back. Let's take a very superficial cut just to check the tracking of the cutter. And with any kind of luck, that is now about 530 across. Let's see what we got. Close enough. I'm going to nibble away at it, and then we're going to take a look at the finished shape and offset for the end radiuses. You're seeing how the sides are formed. I don't see any point in actually showing that. I'll show the finished result here in a second. All right, little change of plans here. I had not planned on showing the removal of the material on the backside, but it's a great opportunity to show how much these cutters can flex. I'm going to plunge, nibble away at this the same way I did the far side, but this is going to be done with the cutter in a clockwise rotation, but in a conventional approach. So if this were an exposed surface that I was creating, this would be a conventional cut. The cutter is going to want to dive in, and when I get to this side, I'm going to pull the rotary table, I'm going to retract the rotary table in a rotary motion back to the starting point, and the finished surface will probably look a lot like that surface back there. It's going to have all these little dig marks in it if everything goes as expected. All right, let's do it. Now, as expected, the rippled surface right there, as you can see, is cutter flex. The outside climb cut, when the cutter returned back to the starting point, was set at the exact same Y position, the exact same X position. The table did not move. The rotary was the only thing that shifted. Each one of these digs is how much the cutter kicks in as it's traveling down. So you can see the advantage of a conventional cut versus a climb cut approach on something like this when you nibble away. Even if you're not nibbling away, you need to be aware that these cutters do flex. Carbide is really hard, but you'd be surprised how much it can actually bend. I'm 30 thousandths away from my final dimension. I'm going to shift the table in 30 thousandths on the Y, take a couple of climb cut finish cuts, and we're going to move on to the end radius. Let's do it. All right. The larger two radiuses of this particular ellipse are complete. Sorry about the Sharpie marker being off center like that. I did that by eye. Let me draw this camera out a second. Ooh, other way, there we go. Let's clean this mess off the table. And the next shift that we're going to do is the entire vise back and forth on the Y-axis, on the X-axis. Orient this true to the machine. The part sits like this. So the X-axis is left and right. I'm going to change the spacer right here. We're going to do the two end radiuses. Stay tuned. Okay, with both of the outer features successfully created, let's put the entire setup back on 0. Since one radius is 750 off center this way and the other was 750 off that way, putting it back on center is a matter of returning to a single 750, 3/4 inch parallel in the back. We're going to move the table back to the 0 position as well. Okay, right now the center of the part is over the center of the rotary table. The center of the rotary table is aligned with the spindle of the machine. Now to do the ends of an ellipse, we're going to have to take this block out right here, and now we'll shift the part to the right. So this is considered a neutral position since we're going to go approximately 408 thousandths in both directions. The center section, the center position would be 408 away from where it's going to ultimately end up. Man, I'm even confusing myself on this one. There we go. We'll take the blocks out. Shift the setup to the right. Now, for anybody that may have rolled the video back to see exactly what that dimension is, the part just shifted 424 off center by removing the block that was down here against the stop. By putting the part 424 off center, the center of the feature that's going to be the round on the end of the ellipse is now over the center of the rotary table. Okay? The spindle is still lined up with what is the center of the end feature. The end feature is lined up with the center of the rotary table. Establishing the size of the radius that you want to put on there is a matter of moving the X-axis and determining, based on the radius of the tool, where to put the cutter. So the first thing you can do is move 125 off, zero out your incremental on your digital if you so desire, and then just dial in the radius. I'm going to go 60 degrees either way on this, and we're going to round that end off and do the exact same thing to the other side. Then we're all going to scratch our heads here, rewind and watch this 14 more times and figure out exactly what the heck just happened. There we go. It's a rough pass. It should be about 20 thousandths away from finish, but let's take a look. Dial it in, finish up. Back to the 0 position. I'm going to double up on the bumper shim that's down here. So in order to get back to center, I would have to go 424 in that gap right there, and then add another 424 to get to the center of the feature on the end of the part. Blow the stuff off, put that shim in there, and continue. Now, like you've heard me say 100 times in the past, the easiest way to create features on a part is to leave the part in the fixture and do as many operations as you can without moving the part. It would be very easy to generate a boss on the top of this and hit 3 points along this part, but that would really not be the demonstration that I want to give you. I'm going to take this over to the saw and I'm going to cut it off and deburr it, and then I'm going to show you how to work with an elliptical shape like this, how to rotationally line it up and get your center fairly easily. A little bit of prep, but once you're there, it's going to fall right into place. All right, let's do it. Okay, fresh off the bandsaw, let's take a look at what we got. I am very pleased with this part. As I stated somewhere in the body of this video, one of these radiuses, there it is, you can just barely see the line right there. Did leave a track mark where the tangent was, and that's either a position of the cutter or a rotational issue or God knows what. Many different ways that could have happened. There's a lot of different ways to do this. Naturally, CNC is like about 7 lines of code and you're done. If you have an XY rotary table, then you're way ahead of the game. And as far as holding this for secondary, naturally, 10 different machinists are going to do it 10 different ways. Depending on how many likes, thumbs up, comments I get about this particular video, I may follow up with a video on how I would approach that. And there really is no wrong way to do it, so long as the feature comes out where it should be in the end. Let's take a look at it dimensionally. See what we got. Looking for 500 on the width. Anything within 5 is going to be acceptable. 497.5. It's about 2.5 thou under nominal. Nominal would have been 500, so I'm about 2 thousandths under that. That's very acceptable for a part like this. 1 inch, 125 long. This one you got to find the high spot because it is looking like an egg. So rock it around until you're happy with the way it's seated and rotate it. 125.5, half a thousandth over max length, also very acceptable. That was a fun part. I hope you enjoyed the video. Hope you didn't get too bored with all the technical stuff in the beginning, but that's all I got for today. I thank you very much for spending some of your time with me today. Wherever you are in the world, I hope you're well and happy and safe and warm. It's getting a little cold these days. Me, Joe Pye, Advanced Innovations in Austin, Texas. I'm out.